Go.
All right, hello. Welcome back to another Mathcounts meeting. Today we're continuing 2016 Nationals. So we're on 17 on Sprint. A rectangular work of art consists of a total of 288 square tiles, each with a length of 1 inch, arranged in 18 rows and 16 columns. If there is a 1/8 inch gap between every pair of adjacent tiles, what is the area of the entire work of art? Express your answer as a mixed number. All right, so what we have here is we have 1 inch tile squares, right? And they're arranged like this, and there are gaps between them, right? So each of these gaps are 1/8 inches long. And then so there are 16 columns of tiles, and there are 18 rows of um, square tiles. And we want to find what's the area of the entire work of art. So the entire work of art is going to be a rectangle. So you can just find the lengths of the sides of the rectangle. So what is that going to be? Well, we have 16 tiles, so just the length of those tiles is going to be 16 times the 1 inches, so 16 inches. But then we have gaps between the tiles, right? So if we have 16 tiles, we're going to have 15 gaps between the tiles. So that means we're going to have to add a 15 times 1/8 length for each of the gaps, right? And then the length of this is just going to be 18 times 8, or 18 plus 18 times 1, 8, oh, not 18, sorry. It's going to be 18 plus 17 times 1/8. And then we just need to multiply these two numbers together. Um, and then how do you do that? Well, you can do it in multiple ways. Maybe we should just keep it as like a mixed number kind of thing. So 15 times 1/8 is 15/8. So that's going to be 17 plus 7/8. And then this is just going to be 20 plus 1/8. So then we can just multiply that together like FOIL basically. So then we'll have 340 plus 1/48 plus 17/8 plus 7/64. So we should try to work with the eighths first. So we're gonna have 157/8. So 160 is gonna be what? It's gonna be 160 is gonna be 20 times 8, right? So this is just going to be 18 plus 5/8. So then we have 340 plus 18 plus 5/8 plus 7/64. So then we have 358 plus 40/64 plus 7/64. And this is 358 and 47/64. And oh, I missed one thing. Oh. Oh, this should be 19. I'm bad. So 160 is 20 times 8, right? So this should be 19. So then this will be 359, and that's our answer. Anything you want to say for that, Bill?
Um, I think that was a fairly simple problem. There isn't really anything to say about it. Yeah.
Yeah. Um, so in the multiplication, you could have also done you could also make it improper fractions and then multiply it, but I mean that's probably going to be worse, right? Because you're going to get very big numbers, and then you're going to have to divide it by 8. I mean, maybe it's probably like fine, but I don't know.
Yeah, the difference in time is not gonna be that significant. So if you do it that way, it's fine also.
Yeah. Okay. Number 18, Marie has an orange that is a perfect sphere with a diameter of 7 centimeters. She cuts her orange into wedges by making 2 cuts from top to bottom through the middle. If one wedge has volume 7 pi centimeters cubed, what is the total surface area of this wedge? express your answer as a common fraction in terms of pi. All right, so what we can do with this is we have the volume of the wedge, right? And we have the volume of the sphere as well because we have the length of the sphere. So we can find the fraction that the wedge makes of the fraction the fraction the wedge is of the entire orange. And if we get that, then we can find like this peel surface area, because then we can just use that same fraction on the total surface area of the orange. And then the inner surface area is not too bad. Those are just circles of the sphere, right? So we can also get that. All right. So yeah, let's find what fraction the wedge is of the sphere. So we need to find the volume of the sphere, which is just going to be the formula is 4/3 pi r cubed, right? So the volume of the sphere is going to be 4/3 pi times 7.
Hi.
Oh, hold on.
Hello? Oh.
All right. So the volume is just going to be this, right? So it's going to be we can just leave it like this. You don't really want to multiply it out because I don't know, you just have big numbers, but like leaving it like this is fine anyway. Okay, and the volume of our wedge is 7 pi centimeters cubed, right? So then we can get the fraction that the wedge is to the entire sphere by making a ratio of the areas, right? Or not areas, volumes. So the fraction is going to be this, right? All right, and then we can cancel the 7 on top and bottom, and a pi. So then we have 1 over 4/3, 7 squared. So then what is that? That's just 3, 3, and then 4 times 7 squared. All right, so this is our fraction. So we can get that peel surface area by using the same fraction on the total surface area of the sphere. So the total surface area of the sphere is going to be 4 pi r squared. So that's a wonky r squared. So the surface area is going to be 4 pi times 7 squared. And we can get the area of this peel by multiplying our fraction with the total surface area. So then the peel surface area will be this times this. We can cancel out of 4 and 7 squared, so that works out nicely. And then we get 3 pi for that peel surface area. But don't forget, we need to get that inner surface area as well, right? Well, again, the inner surface area thing, those are just half circles of the sphere, right? So like if you have the sphere here, these circles, those like half circles, like go through the entire sphere, right? It's like it like it goes through like the middle of the sphere, and the diameter of that circle is also like the diameter of the sphere. So what we would call that is a great circle of the sphere. So like basically that like you can have multiple sizes of circles on a sphere, right? Like you can cut like if you cut halfway into it, then you have a great circle, right? But if you don't, if you cut like only a little bit in, then you have like a really small circle. That's not a great circle, right? But like this part is half of a great circle, and we know that because like this side length has to be the diameter of the sphere. All right, and this is on both sides, right? So basically, we just have one of these great circles in total, right? So basically, we just need to find the area of one great circle of the sphere, and then that will be the like inner side surface area thing. And then we just add it to our peel surface area, and then we'll get our answer. So what is the area of a great circle of the sphere? Well, it's just going to be pi r squared, right? And the radius is 7 centimeters, so that's just going to be 49 pi. All right, and then we just add this to 3 pi, and our answer is 52 pi centimeters cubed. Uh-oh. What did I do wrong, Bill?
Mm, it's with a diameter of 7 centimeters.
Oh, oh yeah, that's gonna mess stuff up.
It does mess stuff up, yes.
All right. Yeah, okay. So don't make that dumb mistake like I did. All right. So let's just do this all again. So our volume is actually going to be, so our radius is half of the diameter, right? So we should have used 7 halves for everything. All right. So this is our total volume. So that means our ratio will be this, and then we will have 7. Wait. Okay. We're gonna have 7/4 times 7 halves cubed. So we're gonna have 2 cubed here, and we're gonna have 7 squared 4/3 here. And then, so this is our ratio, right? And I can bring the 3 on top as well. And then what's our total surface area of the sphere? Well, it's actually gonna be 4 pi 7 halves squared, right? And then we're gonna multiply it by this ratio to get what the peel surface area is. All right, so we can cancel out a 7 halves squared with a like taking out a 7 squared here and a 2 squared there. So we'll have 2 on top there. And we can cancel out a 4 on top and bottom. And then we'll have 6 pi. So the peel surface area is actually 6 pi. And we need to find the inner area, which is again the great circle area thing. So that's just going to be pi r squared, and that's going to be pi times 7 halves squared. So then that's going to be 49/4 pi. And now we add 49/4 pi plus 6 pi. So that'll be 24 plus 49 over 4 pi. And that's just 73/4 pi. And yeah, that's your answer. So yeah, don't don't make those kinds of mistakes.
Yeah. Read the question. Yes.
All
Read
right.
the question carefully.
Anything else you want to say?
Um, I mean, in the end, this is just asking for surface area, which isn't that hard. So there's not really anything much to say, I think.
All right. Let's move on. Exactly 4 of the interior angles of a convex polygon are obtuse. What is the maximum number of sides this polygon could have? All right. So what you can use in this problem is the sum of interior angles of a polygon, like that formula, right? So if you have a polygon with n sides, then the sum of all of its interior angles will be 180 times n minus 2 degrees, right? So like a triangle has 3 sides, so then it'll be 1 times 180. So its interior angles have to sum to 180, which we know is true, right? Okay, so how could we apply that here? Well, we want to find the maximum number of sides this polygon can have, right? So thinking of it with our interior angles, if we want to maximize n, then we also want to maximize the sum of the polygon's interior angles, right? And how could we do that? Well, we know 4 of the angles in the convex polygon are obtuse, okay? And again, we want to maximize the sum of all the angles, right? So we want to maximize these obtuse angles. Um, so what we're gonna do right now is we're gonna make these obtuse angles equal to 180 degrees. Um, like in reality, they're not actually 180 degrees, right? But like we can take the limit as they go to 180 degrees, right? So like we'll leave it as 180 degrees for now. But if we get like some sort of exact equality thing, then we'll have to come back and make sure that like our assumption of the obtuse angles equaling 180 degrees doesn't mess anything up, right? Like if we get an exact equality, then we'll basically have to make this like kind of like 179.9 and see if that like changes anything, right? Okay, but whatever. I hope that makes sense. So right now we're gonna make the obtuse angles 180 degrees, basically like the biggest that they could be, right? And we know exactly for the angles are obtuse, right? So the other angles have to be acute, and we want to maximize those as well, right? So we're gonna make those as big as possible as they can be, which will be 90 degrees, or like the limit to 90 degrees, right? Okay, and so the sum of those angles will be n minus 4 times 90 degrees, right? Because, you know, if we have a polygon with n sides, we're going to have n angles, and we have 4 obtuse angles, so we're going to have n minus 4 acute angles. All right, so the sum of all of our angles will be this, right? And we can equal this to 180 times n minus 2, and we can try to find the maximum n that we can have. And again, if we find an inequality, we'll have to be careful with our limit angles thing. All right, so what can we do? We can divide everything by 90, so then we'll have 8 plus n minus 4 equals 2 times n minus 2. All right, and then we have n plus 4 equals 2n minus 4. And then we have n equals 8. Now, here we have an exact equality thing, right? So again, we have to be careful with our limit thing. So we get n equals 8 if all of our obtuse angles are 180 degrees and if all of our acute angles are 90 degrees. But that's not possible, right? So all these angles are going to be slightly smaller than what we used here. And if they're going to be slightly smaller, that means our n has to be slightly smaller than 8, right? Now, if it's slightly smaller than 8, then the maximum integer n has to be 7, right? So that means our answer is n equals 7. All right, and yeah, that's your answer. Yeah, anything you want to say?
Okay, so for this problem, you can also think about it this way. If you just like imagine, uh, if you just like visualize the four, well, four of the sides are obtuse, so there's five sides. If you think of the five sides, because it's a convex polygon, the and you already have the four obtuse angles, the maximum number of extra angles you can have would be two more angles or three more sides. Like you can have a maximum of three more sides and two more non-obtuse angles, I guess. Because like if you have two 90 degrees, that makes 180 degrees. And so for to uh I guess just for to make a convex polygon, you can only have a maximum of three more sides, I guess. I don't know if that makes sense or not.
Are you
And
still talking about like the sum of the angles?
oh, I
Or,
guess. I guess.
okay,
Eh,
I mean that's like the same as algebra, right?
I guess, yeah.
All right. Okay, let's move on. Number 20, in a word sum, like the one shown, each letter represents a different digit from 0 to 9, with exactly one digit assigned to each letter. If leading zeros are allowed, that is tier zero may be or tier O may be zero. What is the value of that? Okay. Um okay. So each of these letters are assigned a different digit. And they are different digits, right? It says each letter represents a different digit, so it's like we can't have T and H both being one or something. Okay, so we should look at our first column of addition. So we have E plus E plus E is going to equal E. Now, either E equals zero, so that it sums to itself, right? Or we're gonna have some sort of carry here, right? Because if it's not zero, then you can't ever have three of something summing to itself, right? So if it's not zero, then we'll have to have a carryover in it, and the unit digit equaling itself, right? So when is that going to work? We should look at all the cases. So one case is E equals zero, right? Um, so 1, 2, and 3 doesn't work, right? Because there's no carries. 4 is 16, 6 doesn't work. 5 is 15, so that does work. 6 is what? 18, that doesn't work. 7 is 21, that doesn't work. 8 is 24, that doesn't work. And 9 is 27, that doesn't work. All right, so that means our only possibilities are equals 0 or equals 5. Okay, so then what? Then we can look at the second column. So we have 3 more n's, and they're going to sum to e. So let's just look at our cases. So what happens if e equals 0? That means we have 3, so these are all zeros, so we have no carries, and we have 3 n's summing to 0. Or something with the units digit of 0, but that's not possible, right? Unless you had n equals 0, which is not possible because e is already 0, right? So like if you have three digits, they can't ever sum to a something with a unit digit of 0, right? I don't know. That's pretty obvious to me. Yeah, I don't know. I'm not sure how to say that, but n can't be n can't be anything in this case, right? So that means we can't have e equals 0. Um, and you can check that for yourself just by looking at all the n's and seeing what they sum to. All right, so that means e has to equal 5, right? So then we have 1, a carry of 1 from the 15 here. So then we have 1 plus 3n will be a unit digit of e, which is 5, right? Okay, so maybe we should look at cases for this. Or this means 3n has to have a unit digit of 4, right? Okay, so 1, 2, and 3 will not work. 4 does not work. 5 does not work. 6 does not work. 7 does not work. 8 works, right? And 9 does not work. So the only n that works for this will be n equals 8. Because then 8 times 3 is 24, and we have the 4 units digit, right? All right, so then if we have that, we will have the 3 n's plus the carry 1 will equal 25, which matches up with the e, and we'll have a carry of 2. So then we have 2 plus 3, O, we'll have a unit digit of r. And we have no idea what r is. Yeah. Yeah, started 6:30. Okay. Okay. So 2 plus 3, O will have a unit digit of r. Just looking at this doesn't help us too much because we don't know anything about O and we don't know anything about r. What we should be looking at is that the 3 O's plus each other will be THR, and that's very significant, right? We have 3 digits. Um, so like normally you can't have 3 digits summing up to a 3-digit number, right? So that tells us that T has to equal 0, and we didn't use anything equals 0 before, right? So T equals 0 so that we only have a 2-digit number that the 3 O's sum to. Okay, now what do we have? Now we have 2 plus 3 O will equal HR, right? And then we've already used 0, 5, and 8. So now we can just look at this. Um, so H is gonna usually have to be I mean we can just test O's. We could just test O's and see if we get HRs that work. And if it does work, and we haven't used the digits before, then that will be our solution. Right. So um our first case will be O equals 1. So let's check if that works. Well, 5. That doesn't work, right? Because we can't have H equals 0 because we already have T equals 0. So what happens if O equals 2? Well, then it'll be 10, but that doesn't work because we have a 0. We already used 0. 3 will be what? Wait, am I dumb? Yes. If we do 2, it's 8, not 10. But that doesn't work. That's a unit digit, right? And we'll have to have H equals 0, so that doesn't work. Okay. And then O equals 3, then we'll have 11. But that doesn't work because H and R can't both be 1s, right? And then O equals 4, then we'll have 14. But we're saying O equals 4, but then we're saying R equals 4, so that doesn't work, right? We can't have O equals 5, we already used 5. 6 will be, what, 20? That doesn't work because it has a 0, we use 0. 7 will be 23. So this works, right? We have not used 7, we have not used 2 or 3. So this will work, but we can just test the other ones just to make sure. So O can be 8 because we already used 8, and 9 will be 29, which does not work because it has a 9. So that means we have to have O equals 7, H equals 2, and R equals 3. All right, and then we want to find T plus H plus R plus 2E's. So that's just going to be, what, 0 plus 2 plus 3 plus, where's our E? Oh, it's all the way over there. It's NLB plus 2 times, or sorry, 2 times 5. So then this will just be 15, and that's your answer. Yeah. Okay. Anything you want to say there, Bill?
I guess for that problem, what you really just need to focus on is just the units digit. I mean, for E, like if you would know just out of the bat, like right away, that T would have to be 0 and E would have to be 5. Like I think that's something you should just be able to see, I guess. But I mean, other than that, this problem is, I guess, kind of straightforward. There's nothing besides the stuff Austin has already said. So,
All right. Let's move on. Number 21. Manny has 2 red socks, 2 white socks, and 2 blue socks. He plans to choose 2 socks at random to wear today. 2 of the remaining socks to wear tomorrow, and will wear the last 2 remaining socks the last day. What is the probability that on all 3 days Manny wears 2 different colored socks? Express your answer as a common fraction. All right. So, so Manny has 2 red, 2 white, and 2 blue socks, and he takes 2 every day, and we want to find what's the probability that on all 3 days he'll wear 2 different colored socks. And so he uses remaining, right? So it's going to be like without replacement. Okay. So without loss of generality, we can just assume the first sock Manny picks will be red. Okay. And then we will have 1 red, 2 white, and 2 blue. And then what's the problem? So he has to select white or blue to have different colored sock, right? So that probability is just gonna be 4/5. So that's just for the first day of socks, right? So again, without loss of generality, we can assume that he chose white, okay? And then we'll have red, white, and 2 blue for the second day. And then we can look at cases here. So he can either select what? He can select red, white, or red, blue, or white, blue. Technically, without loss of generality, the red, blue, and white, blue are the same case, but whatever. Okay, so the red-white case will not work, right? Because if we do red-white, he will have two blue socks for the next day. And he can't have two of the same color, right? So that's not gonna work. And like I said, these are just the same cases, kind of, right? So basically, like we have to choose one of the red or white socks, and we need to choose one of the blue socks. Okay, so what's the probability that that's gonna happen? Well, um, so the first sock that you choose will be like any of these, right? So that doesn't affect anything. So so I don't know. So you're either gonna choose a red or white sock on your first thing, so then you'll have something and then two blue, or you're gonna choose a blue sock and then you'll have red, white, blue. Okay. Sure, we can separate that into cases. So we have two red, white, and two blue, right? Which means we're gonna have equal probability of selecting either red or white or one of the blues, right? So we can just have the hash for those initially. Okay, so let's say this is the case where we choose red or white. Okay, and then without loss of generality, let's say that we chose red in this case. So then we have white and two blue. And because we chose red, we need a blue. So then that will be 2/3. In this case, we chose blue first. So then we'll have red, white, and blue. And because we chose blue, we need to choose red or white, but that's also 2/3, right? So then our probability will just be 1/3 plus 1/3, which is just 2/3. Okay, so our second day will be 2/3, no matter what, right? Because our first day was just one case, and our last day, what will we be left with? We will be left with like already different colored socks, right? Because we already ruled out the case where it gives you matching socks. So that means our last day will be 1, right? So then we just multiply these together and we will get 8/15. And yeah, that's your answer, 8/15. Um, yeah, listing can also work, I guess. Um, Anything you want to say, Bo?
Right, listing would definitely work, and listing might be feasible because this on such a small scale. You can probably get away with it, but it's probably best to just do it using probabilities. Mm. And I mean, if you look at this problem, the only way to have him wear two different color socks on all 3 days is, if he wears like a different combination every day, red, white, white, blue, and then red, blue. So yeah.
Yeah. Uh, yeah, yeah, listing can definitely work. All right, let's just move on. It's a fairly simple problem, and not that bad. So, you know, yeah, you can do it multiple ways. It's fairly easy. All right. Number 22, if two positive integers a and b are relatively prime, then the quantity a times b minus a plus b is called their Froben, uh, Frobenius number. If b is 2 more than 3 times the value of a and b have Frobenius number 3, what is the value of a plus b? All right, so it's saying b is 2 more than 3 times a, right? So we can just substitute this into the Frobenius number formula, and then what? And then our value will be 2a plus 3a squared minus 4a minus 2, and this will be 3a squared minus 2a minus 2. So this is their Frobenius number, and it tells us that this is equal to 223. So we can try solving for a like this. So then we'll have 3a squared minus 2a minus 225 is 0. Okay, and then so we should look to see if we can factor this. So we can look at the factors to 225. So this will be 45, and this will be 5 and 9, and 3 and 3. So so does anything work here? Oh yeah, it actually does work. So if we use 9, if we use 9 and 25 here, we can use the 3 to triple the 9, so we have 27, and then this will have a difference of 2. So we can factor this as 3a plus 25 times a minus 9. So then we have 20 minus 27a, and we have 25a. So then we'll have minus 2a, and we also have the minus 225. Okay, and then a is a positive integer, right? So it can't be that. So a has to be 9. And there you go. You've got an a, and then for b, it's just going to be 29. So then you just add those. So that's just 38. So that should be your answer. Yeah, that's your answer. Yeah, this one is pretty easy. Yeah. Anything you want to say there, Bill?
Okay, this one, there's not really anything. It's just you plug it in, so
Yeah.
you just plug it in.
All right. Let's move on. Number 23, circle O has radius 4 units and point P lies inside the circle, 2 units from center O. Circle O prime is the image of circle O rotated counterclockwise 90 degrees about point P. If circle O prime intersects circle O at points M and N, what is the length of segment MN? Express your answer in simplest radical form. All right, so we have some sort of geometry problem, so we should definitely draw a figure here. So let's just start with circle O. It has the center of O, and it has radius of 4 units, okay? And then point P lies inside the circle, 2 units from center O, somewhere. But without loss of generality, we can just put point P like right here. And it's going to be 2 units away from O. Circle O prime is the image of O rotated counterclockwise 90 degrees about point P. So using point P as reference, we're going to rotate circle O counterclockwise this way 90 degrees. So our new center O prime, actually, will have to be like right here, right? Because we're rotating about point P. And then circle O prime will intersect the circle O at points M and N, and we want to find that length of the segment. Okay, so one thing we can do is make a coordinate plane, and we just have it we have our origin at point P. Okay. Um. All right, and then we're gonna rotate circle O counterclockwise about point P, and this circle O prime will be like what? It will be like right here maybe. And it intersects at points M and N. Okay. Um, and this length will also be 2. Um, oh, okay. So one way you could do this is coordinate dash, right? So we know the radius of the circle O. We know where it is in our coordinate system. So we can find the equation for that. And we also know that circle O prime will have the same radius, and we know where its position is in the coordinate plane. So we can also get the origin for that circle, right? I mean, the equation for that circle. So then we can use those two equations, coordinate dash, to find 2 points, and then use the coordinates of those 2 points to find the length of that segment, right? Um, okay, so let's try that method, right? So the equation of O will be what? Will be x plus 2 squared plus y squared equals 16. And O prime will be x squared plus y plus 2 squared equals 16. And then we can try to solve these. So what can we do? We can subtract them, or sure, we can subtract them, and then we'll get like a line equation. So if we subtract them, like this one from this one, we'll get we have 4x here, and we have a plus 4 there. And then we'll have plus y squared, so the x squareds cancel, and then we'll have minus y squared minus 4y minus 4, and this will equal 16. So the y squares also cancel, and the 4's cancel. The 16 is not here. These cancel, right? So then we have 4x minus 4y equals 0. So what's this? This is just y equals negative x. So this tells us that the intersections are on y equals negative x, and this makes sense, right? Because of symmetry. Um, so then we can find solutions by just substituting this into here. So we can have substituting y equals negative x to this, you'll get x squared plus 4x plus 4 plus x squared equals 16. And then we'll have 2x squared plus 4x minus 12 equals 0, or x squared plus 2x minus 6 equals 0. And then can we factor this? No, we can't, right? So it's going to be radicals. So that's fine. These are just oh, actually, yeah, yeah, it should be y equals x. My bad. I just got messed up with the negatives there. So yeah, that makes more sense, right? Y equals x is like that. All right. This actually doesn't change this though, right? It's still x squared here. Yeah. Okay. And then we can just use quadratic formula here. So x is going to be negative 2 plus or minus 4 plus 24 over 2. So this will be 28. We can take a 4 from that, and that will cancel with a 2. So that will be -1 plus or minus root 7. So these are our x's for these points, right? And then what's going to be the y? Well, y equals x, right? So the y points are also going to be -1 plus or minus 7. Okay, and then we want to find the length. So we have the points like root 7 minus 1, comma root 7 minus 1, and negative root 7 minus 1, comma negative root 7 minus 1, right? So our distance is just going to be this minus this squared plus this minus this squared over a radical, right? So this minus this is just going to be negative 2 times root 7. I'm going to square that, and this will also be negative 2 times root 7. And then we need to square root it. So what is this going to be? Well, it's just going to be 4 times root 7, and we need to root that, right? Oh, actually, no, I'm bad. It's going to be 4 times 7 plus 4 times 7. So this is 8 times 7. So then we have the root of 8 times 7. So we can take out a 4 from that. So we'll have 2 times root 14. So this should be our answer. Yeah, that's right. So 2 times root 14. Um, yeah. Anything you want to say there, Bill?
Well, so something you could see is that well, you could see that boo to this problem too much bash. Well, you could just see that this problem, the line between n and m will be y equals x because the circle itself, it's rotationally symmetrical. So when you rotate it, it's not going to change. And so when you rotate it counterclockwise 90 degrees about point P, you're in essence just shifting it down and to the right two and down two and to the right two. So the intersection between those two circles will be on y equals x. Will be on the line y equals x. Yeah. And
Yeah.
yeah,
Um, yeah, coordinate bash is probably the best way to do this.
yeah, most likely it
You
is.
you might also be able to solve it with geometry, but that's just kind of, I don't know.
I mean, you probably could. I would think you could, but yeah, it'll be
Uh,
kind of hard.
maybe you could.
Maybe
Um,
maybe I wouldn't recommend it, but you're probably just better off sticking with the coordinate batch for this problem. So
yeah. Wait, actually, maybe you can do it geometrically easily. Wait, let me see if this will work. So O and O are here, or O and O prime are here, right? So we know, so M and N are here. Maybe I should just use this figure. I'll just use this figure. So we know that these distances are 4, right? And this is 2, 2, and 2 like that, right? So this distance will be, what? Will be 2 root 2. And then we want to find the length of this segment, right? And then we're going to have um, we're going to have a right triangle here, right? It's going to be, this whole thing is 2 root 2, right? So this will just be root 2, and this hypotenuse will be 4 from here. So then we just Pythag, it will be 16 minus 2 rooted, which is root 14 here, right? and this is the length of that segment, right? So then you just double that. So then it's 2 times 314. That's what we got earlier. Okay, so you can also do it geometrically, and that's not bad either. All right, let's move on. If x, y, and z are real numbers such that 4 to the y is x, x to the 1 plus y is 8, and 2x equals 2 to the z, what is the value of z squared? All right. I mean, I would just think to substitute everything into each other, right? Um, so what should we start with? We can substitute x equals 4 to the y in here. And that might also work well because we have like a lot of 2 to the power stuff, right? And then maybe we can cancel stuff out. So we'll have 2 times 4 to the y equals 2 to the z. And 4 to the y is just 2 squared to the y, right? And this is just 2 to the 2y. So then that's just 2 times 2 to the 2y, which is just 2 to the 2y plus 1, right? So then we have 2 to the 2y plus 1 is 2 to the z, which means that 2y plus 1 will equal 0. So that's nice, I guess. And then what? And then maybe substitute x into here as well. So we'll have 4 to the y to the 1 plus y. Oh, 4 to the y, not there. That's okay. 4 to the y to the 1 plus y will equal 8. So this is saying what? This is saying 4 to the y plus y squared equals 8. Well, what is this? We can use the same 2 squared thing, right? So we're saying 2 to the 2y plus 2y squared equals 2 cubed. And we can use the same thing to say that 2y plus 2y squared equals 3. And then we can use this to solve for y, right? And then use that to solve for z. We'll get 2 solutions for y. Oh, maybe we'll get 2 solutions for y such that z squared is the same thing. I think we should still just try solving for y here. But yeah, so we're gonna have 2y squared plus 2y minus 3 equals 0. So quadratic formula, we have y equals negative 2 plus or minus 4 plus 24 over 2. This is like the same thing we had last time, right? You have negative 1 plus or minus 7. Yeah, see. And then when we, oh wait, actually, what? Uh, uh, actually, that's not so nice. We have y equals negative 1 plus or minus 7, right? Um, no, yeah, it should be 4 plus 24. Um, okay. Um, did I do something wrong here? Isn't the plus 1 supposed to, like cancel out with the, wait, what are you guys saying? Uh, isn't what plus 48? Wait, Bill, what are they saying?
Oh. Oh, just said never mind. It's not. Don't mind me. Okay.
Wait, but we did make some mistake here, right? Isn't
Yeah.
like the negative one supposed to cancel out with the
The
plus one?
discriminant is the discriminant is 24. He says.
Like this whole thing is 24?
No, it's 28.
Okay.
Uh,
Um,
trying to do.
okay. Did we make any mistake here? Maybe we made a mistake with this. Um,
I highly doubt it. I mean, I don't think
uh,
we did.
okay, so if we use these, then what do we have? We have negative 2 plus or minus 2 root 7 plus 1 is z. So then we have negative 1 plus or minus 2 root 7 equals z. See, that's not nice, right? Because if we square it, we'll get different things depending on what the plus or minus is. Uh, okay, maybe we should just check our work, right? So we substituted x in both these equations. So we have 2 times 4 to the y is 2 to the z, right? So this is 2 times 2 to the 2y equals 2 to the z. So then this is 2y plus 1 equals z. So that should be correct, right? And we also substituted x in there. So we have 4 to the y to the 1 plus y equals 8. Um, and then what? We can put this y there. So we'll have 4 to the y plus y squared equals 8. And then we can take a 2 squared here. So then we'll have 2 to the 2y plus 2y squared equals 2 cubed. And we get the same thing as last time, right? Uh, oh, wait. See, this should be over 4, right?
Yes,
Um,
it should.
I like how none of us saw that. Um,
Absolutely not. I saw that. But would that make a difference?
yeah.
Would that make a
Oh,
difference?
no, yeah, that makes a huge difference.
Oh,
Because then when we had what? We had 2y plus 1 equals z. So now when we do that, we'll have negative 1 plus root 7 plus 1 equals z.
oh,
So then
that
the
does
negative
make a
ones and the
difference.
ones
Yeah.
cancel, which is what we needed, right? So then z is just plus or minus 7. So when we square it, we just get one thing, which is just 7. Yeah. Oof. So
Oh,
many mistakes
it
today.
was
We
just
need to get better.
one single silly mistake. Oh man.
Silly, silly. Um,
Oh, it's all just.
yeah, all of our meetings are on YouTube, but Ishan already left. Okay. Yeah, so far these problems are kind of messy. So, I don't know, yeah. Okay, let's move on. Number 25. What common fraction is equivalent to 1 over 1 cubed plus 1 over 3 cubed plus 1 over 5 cubed plus dot 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 over 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus dot dot dot. All right. So, um, so first you can think, will my geometric series formula apply to this? And if it does, then it's pretty easy. But it doesn't, right? Because these are 1 over natural numbers cubed. So like the ratio between each of the things is not common. If it was common, we can use the formula. But it's not, right? So we can't use the formula. All right. So what are we gonna do here? So um, so one thing we can do is we can generalize the sums of each of these. And what do I mean by that? So I can say the sum of this thing is the sum of n equals 1 to infinity of 1 over n cubed. And I can say that the sum of this is the sum of n equals 1 to infinity of 1 over 2n minus 1 cubed. Um, yeah. Okay. And then what? Yeah. Oh, okay. So wait, actually,
For this,
oh, okay, I got it. I got it now. I got it now. Okay, so this is actually pretty hard, yeah. So we can what we can do is we can also make a summation for n equals 1 to infinity of 1 over 2n cubed. So what is this the sum of? This is 1 over 2 cubed plus 1 over 4 cubed plus dot dot dot, right? Okay, so what is this sum gonna be? Well, it's gonna be this sum minus this sum, right? So we can say that that sum on top, we can call that x. That will be the sum of n equals 1 to infinity of 1 over n cubed minus the sum of n equals 1 to infinity of 1 over 2n cubed. Now, why is this really good? Well, it's because this thing right here, it's the sum of n equals 1 to infinity of 1 over 8 times n cubed, right? And because this 1 over 8, is just a constant, we can get it out of the summation, right? So this is 1/8, the sum of n equals 1 to infinity of 1 over n cubed. And this is really good, right? Because we have this exact same thing right here. So then we can say x equals 7/8, the sum of n equals 1 to infinity of 1 over n cubed. Now, this this thing right here is just this, right? And x is that, right? So then our fraction will just be 7/8 times the sum of n equals 1 to infinity of 1 over n cubed over the sum of n equals 1 to infinity of 1 over n cubed. So then these things cancel. So then we just get the nice 7/8. And that's your answer. Yeah, that's your answer. Um, so the thing with this is when you're working with infinite sums and stuff, uh, you want to see if you can generalize stuff. and see if that you want to see if you can put stuff in series notation and see if that will help you like simplify or do things, right? Like especially when infinite sums, that's really important. And then the key thing was noticing that this 1 over 2n cubed is really nice, right? Because it's going to be 1/8 of 1 over n cubed. And then noticing that this we can just put it in terms of that 1 over n cubed and this 1 over 2n cubed. Yeah. But this is pretty hard to come up with. I would say this is pretty hard for a math counts problem. Anything you want to say there, Bill?
Well, so to get an idea of how hard it is, uh,
Oh
17
wait,
people, 17
yeah,
people
we
got
have
it right.
the
We have the score
yeah,
distribution.
we can pull that up.
17 people got it right at nationals. So, just get an idea of how hard it is. Um, but yeah, for this problem, something you can probably just like something that what you can notice is that, you have like the top is similar to like one half. Like the top
Yeah,
numbers
okay.
are it's the top is every other number and the bottom is all the numbers. So you would like think that, there's one half involved in there somewhere. And so
Yeah, looking at the score distributions, you can see that this problem was really tough, right?
it was
Only
very
17
hard.
people got it right. Um, yeah, this is pretty cool to look at. Um, apparently number 4 was really hard, but I don't know. Me and Bill thought it was not that hard. We can go back and look at it. Where is it? Let me put this like right here. Number 4. It was the you have 3 fractions, you have plus and divide. And you wanted to make the biggest fractions and the smallest fractions. Yeah, that's not too hard. Not where you have a huge jump, 229, 207. Yeah, that's kind of weird, I think. But yeah. Um, yeah, 25 is pretty hard. Um, you just have to notice that really nice thing. All right. All right, let's just move on. Number 26. Let's do here. For positive integers a and b with a squared over b cubed equals 9 factorial, what is the least possible value of a over b? Okay, so what we should try to do here, or one thing we could do is put this as a over b squared times 1 over b equals 9 factorial. So why do we want to do this, or why do we want to try doing this? Is because we're trying to minimize a over b, right? So if we could get our stuff in terms of a over b, that might help us out. Okay, and so we could try getting over to b by itself, right? So we can put the b on the other side. So then we have 9 factorial times b, and then we have a over b equals the root of 9 factorial times b. So, if we can just minimize this, then we can already just minimize a over b, and we can try to get our answer, right? All right. So let's think about this here. So So we have this is always going to be an integer, right? A and B are positive integers, and 9 factorial is definitely an integer. Um, yeah, we should try prime factorizing 9 factorial. So we're gonna have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So this is I'll make tally marks. 2, 3, 4, 5. What? Not a 4. 2, 3, 5, and 7. So we're gonna have 1 there, 2 there, 1 there, 1 there, 1 there, 1 there, and 1 there. So we're gonna have 2 to the 6, 3 to the 4, 5, and 7. Okay. Oh, did I? Yeah, whoops. That should be 7. So many mistakes. Okay. Okay, so we can get these out of the radical directly, right? Like these. So we have 2 cubed times 3 squared. Then we have the root of 2, 5, 7, b. Okay, and what does this mean? Well, this means a has to have at least 2 cubed times 3 squared, right? For this 2 cubed and 3 squared to come from. And it's going to have more, right? Um, so yeah, so the stuff that we get out of our radical has to be like we had to get rid of this radical entirely, right? Because we just have positive integers a over b. We're never going to get radicals out of this, right? So we have to get rid of this radical. And what does that mean? That means b has to have at least 257. And it could have more. But would more help? Maybe not. We can look at that. So we should just go ahead and use this 257. So so we're gonna get a 2, 5, and 7 out. So then I'll call the rest of bx if we ever need it. So then we'll have a over 257 over x equals that. Okay. And then what do we have? We have, so if x is just 1, there's no part rest of b. Then we have a is 2 to the 5th, 3 squared, 5 squared, and 7 squared. Um, Actually, is that right? Oh, I'm actually kind of bad. Yeah. So we're just looking at a over b, right? So I shouldn't have tried to put this into a at all. So like we're literally just looking at this part. Like we're just trying to minimize a over b. So like, we don't even have to like consider anything into here. So we do want to minimize b, right? Because the like we want to minimize this, right? So we want to minimize b. So then this is pretty easy, right? So then a over b, the minimum of it is just going to be 2 cubed times 3 squared times 2 times 5 times 7. Yeah, okay. And then you can just multiply this out. It will be 2 to the 4th times 3 squared times 5 times 7. So this will be 40 times 63, which is then 2, 5. Uh-oh. I think I made a mistake somewhere again. Oh, this is 16. Whoops. Oh my gosh. I'm just making so many mistakes today. Okay. So 16 times 5 will be 80. And then times 9 times 7 is 63, right? So then this is 48 plus 24, which is, or yeah. So it'll be 504 and then an O at the end. Okay. So this should be our answer. Yeah, it's 5040. Yeah, so when you get to this point, just look at minimizing this, right? You're just minimizing A over B, so you don't need to like look at that at all. Yeah, that was pretty easy. Um, you just had to get the A over B out of this first, and then it's pretty easy. All right. Okay. An ant sits on one face of a cube. 1 minute later, the ant has moved to a random adjacent face. If every minute the ant randomly moves to an adjacent face, what is the probability that after exactly 4 minutes, the ant is on its original face? Express your answer as a common fraction. Okay. So the ant is going to move 4 random moves, and we want to find the probability that it's on the original face. So without loss of generality, um, it's going to go to some, I don't know, we can just make it the top face. Okay, so we can make this the starting face, and without loss of generality, we can say the ant goes to this face right here. And then where can it go? It can go back to the start, to one of the side faces, and to that face, the opposite face over there. Okay, so let's look at the side face first. So the probability that the ant will go to the side face is 1/2, right? And after that, it will have 2 moves left. Now, in those 2 moves, it has to move to another side face and go back to the start face, right? You know, if it goes to opposite face, it only has 1 move to get back to the starting face. That's not going to work. And if it goes on the starting face, it has 1 more move and it can't go back to the starting face, right? So what does that mean? It has to go to one of the side faces and then it has to go to the starting face. So going to one of the side faces will be 1/2, and then going to the start face again will be 1/4. And then so we should look at the what happens if it's on the start or the opposite face on the second move. So let's look at the opposite face first. Opposite face will be a 1/4 chance. And then on the opposite face, we'll have to get to the starting face in 2 moves. So we'll have to go to some face and then go back to starting face, right? So going to any of the face is just going to be 1, right? And then going back to the start face will be 1/4, right? And then what happens if we go to the start face on the second move? Well, the probability of that is 1/4. And then what do we have to do? We have to go to some start face. We have to go to some side face, and then we have to go back to start face, right? So that's like the same thing as opposite face. So 1 is any of the side face, and 1/4 will be it coming back to the start face. So then we just sum all of these together, or all of these are 1/16, right? So then we just have 3/16. Yeah, that's your answer. This one is pretty easy, I think. Um, yeah, it's really not that hard. Like especially you only have 4 moves, right? So it's not that hard. You don't have many cases either. Um, yeah, 37 people solved this. So oh no, it was actually 19. I don't know. I wait. This is actually like almost the same difficulty as the summation problem. I think that's kind of weird. Maybe less people solve this because it's a little bit later and less
Yeah,
people get to the end.
yeah, maybe
But
they
I don't
just
know.
did not get to the end. So
But I mean, they're only separated by 2 problems. I
that's
don't know.
true. Maybe they got
This
stuck on 25. I don't know.
I think this one is really easy compared to 25.
Yeah, it was.
Yeah, maybe people spent more time on 25.
Yeah, Don't do that. If you
because it
spend
came earlier.
if a problem was too hard, just skip it. Don't take too much time on a
Yeah,
problem.
if a problem is too hard, definitely skip it. Um, and there can be like there could be like really hard problems like earlier than you expected.
Yeah.
Like just like if you can't solve a problem, just skip.
And also
And
sometimes
like
they'll put not like extremely hard problems towards the end just for people like just in case you get there. Sometimes they'll do that. So,
yeah, so like yeah, if you can't solve questions, skip it and like try to work through the whole test. And then the extra time you have at the end of the test, then you go back to the problems that you skipped earlier. So like skipping is a real like a really good strategy that you should apply, right? Like instead of like trying to solve every problem individually and then maybe you don't have time for the last problems and then maybe like some of those are easy, you know, and you don't even have a chance to like try to solve them. So yeah. All right. Okay, let's move on. Number 28. What is the remainder when the sum of 1 squared plus 2 squared plus 3 squared plus dot 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 plus 2016 squared? Oh, you're saying mods. Yeah, mods are probably good here. But I think there's actually like a better way to do this that I really like. So, there's the sum of square integer formula thing, right? Do you know that? It's like if you have 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared is what? N times n plus 1 times 2n plus 1 over 6. So this is really good in our mod thing, right? Because looking at this mod 17 is really easy, right? So we can just do that. So this will be 2016 times 2017 times, I'll just leave it at this, 2 times 2016 plus 1 over 6. So we should look at, like, we actually don't need to expand this, right? If we just find what 2016 mod 17 is, then we can put that into there. So that I don't know, that just gives you, or I don't know, that saves you a little bit of arithmetic, but whatever, right? Okay, so 2016 mod 17 will be 316, and then it will be 146, and then what? And then you can take out 17 times 7. Uh, actually another 17, so 136. So then you have 10. So 2016 should be 10 mod 17. So then 17 will be 11 mod 17. So then this will be 20 plus 1 mod 17. So 21 mod 17, so that's just 4 mod 17, right? Over 6. Um, we actually get a dividing by 3? Oh, right. Okay, so this is kind of weird. So, okay, so if we do this, we will have, what? We'll have, like, sure, 5 times 11 times 4 over 3. So this over 3 is weird because you can't simplify anywhere, right? But you actually can with mods. It's kind of weird, right? Like, you can add 17 to any one of these top integers to try to get it to a multiple of 3, and then canceling that with the 3. So like this 4, you could add 17 to it, right? That doesn't change anything. So then it's times 21. And then the 21, we can get rid of a 3 in it. So then this is equal to 5 times 11 times 7 mod 17. I think that's kind of cool, actually. Okay. Um, yeah. So then we have, what? 55 times 7 mod 17. So then, we can take a 34 out of this. What, 21 times 7? And then we'll have 4 times 7, so then it's 21, and then 4 mod 17. Whoops. No, I actually did it wrong. Yeah, I got it wrong. Uh, yeah, probably some computation error somewhere.
Yeah, there
Um,
were a bit of a computation involved. It probably is just computation.
Man, I'm making so many. Yeah, I'm making so many sillies today. 2016 is 10 mod 17, right? Perhaps. Yeah, it is. So then, I think this should be right. Oh, you found it? Uh, in the 55. Oh, okay. Yeah, you can't take out the 34 from the 55. If you just look at 55 times 7, then that's 11 mod 17. Um, wait, Bill,
Yep.
am I dumb? Like, why does that not work? Like, why can't you take, I don't know. Like, can't you say, oh no, like 55? Like, if you take out a
Um,
17, I don't know.
I'm. Oh.
Uh,
Oh. Is that
or like what I was thinking is like you could put 55 as like um what 38 plus 17 times 7, and then like you put that out, right? But the 17 times 7 is just going to be 0 mod
Okay, Austin,
17.
Austin, look, Austin. I think I found your
Oh yeah,
problem here.
yeah.
In what universe does 4 times 7 equals 21?
Oh, oh, oh,
Now, if
yeah.
you get 28, that's 11 mod 17.
Oh, oh, yeah. The whole time it was just that.
Right. So for 1001, the you can't just you
Yeah,
are able to just take 34 away from 55 because
yeah,
in essence what you're doing here is also just 7 times 55 mod 17, like 7 times parentheses 55 mod 17. So you can just,
yeah. Like,
take away.
like if you look at this, what I was saying, like you put 55 as something plus 17, right? And then you distribute the 7. and this is gonna cancel out in the end, right? So yeah, it was just the darn 28, you know. So yeah, that's 11 mod 17. So many, like, I don't know, just the simplest mistakes today. So many. Yeah, maybe it's because today's problem had been like so messy, kind of. I don't know, but maybe I'm just bad. All right. Yeah, that was number 28. Um, it shouldn't be that bad. I don't think. Well, if you know the formula, if you know the formula, it should not be that bad. Um, yeah. All right. Number 29. Octagon ABCDEFGH, shown here, has eight equal sides of equal length, and ACEG is a square. If the area of square ACEG is 7/9 of the area of the octagon ABCDEFGH, what is the ratio of the area of square BDFH to the area of octagon ABCDEFGH? Expression answers a common fraction. All right. So um we can start by assuming the area of the octagon is 1, right? And then what? Uh, we should draw a figure, or let me copy the figure down. Oops. What? I just drag this onto here. Okay. Oh, it does work actually. All right. So yeah, let's say the area of the octagon is 1. Um, and then so this is not a regular octagon, right? We know the sides are of equal length, but we have no idea what the angles are. And it makes sense that way, right? If it was a regular octagon, then the squares would be the same. So then you would just have the same area ratio. So what can we do here? We should start by saying the sides are x, and then try to work through some stuff here. So if our side is x, um, wait, actually, uh, what? Um, yeah, these are all isosceles triangles. Like all of these sides are x, right? Okay. Why don't we just? Oh, okay. Why don't we just label this as y for now? Um, did we do this in our working out thing, Bill?
We did.
Was it?
We used
Did we
trigonometry.
do it this way?
Uh,
Didn't we do something like really easy in our thing?
we didn't we use like did we use like law of cosine or something?
What?
We use like law of cosine or something.
I
Like
don't
we
think
used
so.
trigonometry, I remember, for some reason. Did we?
No, I think we were wanting to use trigonometry, but
Oh
like
right, we were
it
wanting
just
to do that.
wasn't good. Okay, sure. Well, let's just do this for now. Let's see. This is X, this is Y.
Oh, I suggested coordinate bashing for some reason, I think. No,
Oh,
no.
what?
Never mind.
I don't think
Just
we did.
yeah, just
Yeah.
ignore it. I don't think they coordinate bash this. No, please, no. Okay.
Okay, sure. This is Y. Um, I don't think we did this in our thing because then this is not nice. This is X squared minus Y squared rooted. I don't think we had that. Okay, Mister, let's just do this. I don't know. Oh, okay. So the areas of these triangles will be 1/2 y root x squared minus y squared, right? Yeah, this is not nice actually.
Well, we can I guess we can set these to something. Because we can just have the whole entire the area of the entire octagon be one, and then have the square be 7/9.
Oh wait, okay, sure. Let's make the octagon area of the octagon like 18. Okay. So the area of the oh okay okay. The area of the oh yeah, I'm bad. Okay, yeah, this is actually pretty simple.
No,
So
you're right.
look, if the area of the octagon is 18, right? The area of the square is going to be what? 7/9 that, so 14. So that means each of the square side lengths will be root 14, right? So that means we like already have y, right? I put y as a variable, but I didn't need to. So then everything should be fine, right? So that little length is going to be but I'm still gonna have the sides as x, right? So y is gonna be root 14 over 2. So that's gonna y squared is gonna be 14 over 4. Okay. Um sure. And then that's gonna be x squared minus 7/2 rooted. Okay. And then and then oh okay. So what we can do is actually does that help? So we know that this length is root 14 over 2, right? To the center from here to here. So then we know that this whole length is that plus root 14 over 2, right? Um so this is the diagonal the uh of the square thing, right? So so then the area of the square thing will be this over root 2 squared, right? That's not too nice. I think we have to find x here. So we can just try to find the area of the things. So the areas of the triangles have to be 4, right? Because this is 18, this is 14, right? So each of the triangles have to be area 1. And the areas of the triangles are 1/2 times x squared minus 14 uh, over 4 times times what? Times root 14, like that. And we have 2 equals root 14x squared minus 7 times 14 over 4. So then we'll have 4 equals all that. Or not 4, this will be 2. Yeah. Um And this will be 49. Okay, so then we should be able to solve for x, right? Oh, it's actually just what? Yeah, it's actually just 14x squared equals 53. That does not seem right. Do you remember having numbers like this?
Oh, this was a while ago. I don't remember anything.
Yeah, we did this a while ago. Maybe I did more arithmetic wrong. That would be really sucky. I feel like today's just a bad day. I don't know. Okay, sure. Let's just say x equals root 53 over 14 for now. Okay, so then this will be the area of our new square, right? So then it will be 53 over 14 minus 7 halves. I don't remember having wacky numbers like this. So is this nice at all? It'll be, oh, I think that is nice actually. So we have 53 minus 49 over 14, right? Okay, so that's not bad. Root 2, and then we're going to square that. So this is going to be equal to 2 over root 14 plus root 14 over 2 over root 2 squared. So then this will be 4 plus 14 over 2 root 14, I think, over root 2 squared. This should lead to our answer if I didn't do any arithmetic wrong. So then we'll have 18 over 2, or it'll be 4 now. It'll be 4 root 7 squared. So this will be 9 over 2 times root 7 squared. 81 over 28? I don't think that's right, actually. Oh, wait, we had to put this over 18, right? So we said our thing was 18. Does that help? I don't know. So it's going to be 81 over 28 over 18. So let's get a 9 out of them. And, or what, times 2. And this is 9 over 56? I don't think that's right. Let me see. 9 over 14. Hey, we were
We're
kind of close.
close. So that probably
So
means
it
that
was
we,
definitely computation error
yeah,
somewhere.
confirmation error. When you get like something like that, that's definitely confirmation error.
So many computation errors
Well,
today.
we
I just
it is
can't.
well these the past few questions have been really just calculation heavy, and when you're doing it by hand, it's real. It is easy to make mistakes.
Which we do. I think we should just start over. Just do all the arithmetic again. Yikes. 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 All right. Let's do it all again. All right, come on. Speed run this time. Okay, so we're going to say the octagon area is 18. Just assume it's 18. So the square that we have will be area of 14. That means the side length will be root 14. And so we have the triangle. If we say the sides are in length x, we have the triangle x and root 14 here. So um, this side length will be root x squared minus 14 over 4, which is 7 halves. Yep. And then the area of this triangle will be 1/2 times root 14 times root x squared minus 7 halves. And this has to equal 1 because the triangle is equal 1. So then that means 14x squared minus 49 will equal 4. Okay? And then we have x squared equals 53 over 14, or x equals root 53 over 14. Okay. And then this is root x squared minus 7 halves, right? So then that is root 53 over 14 minus 7 halves. This is just 2 over root 14. Now we know that that length is... Oh, wait, I think I see it now. I think I used that was the whole diagonal, but I only got half of the diagonal. Okay. So if we add this to that length right there, which is root 14 over 2, and then we double this will be the diagonal of our BHFD square, right? So this is what? This is 4 plus 2 root 14 over... No. This is 4 plus 14 over 2 root 14 times 2. Yeah. So this 2 should be our original answer times 4. I'll just do it all again though. So this will be 18 over root 14. Okay, this is the diagonal. So we put it over 2 to find the length of the square, and then we square it to find the area, and we'll need to put that over 18 at the end. Or we can just put it over 18 now. Okay, so this is our expression. It's 3 stacks of fractions. All right, so this will equal 18 over 2 root 7. We're going to square that over 18. This will be 18 over 49 times 2, right? Actually, what? Uh-oh. Hold on. Oh, this should be 4. Wait, that doesn't help. Oh, this should be 7. Oh my gosh. Oh my gosh. I'm just being so bad today. Okay. The square of 2 times root 7 should be 4 times 7. So then this will be 9 over 14. Let's go. We finally got it. All right. That was rough. So if you just utilize that diagonal thing, you you just have to make sure not to make any computational errors, and then it's not that bad. But we did make a lot of computational errors. All right, let's move on. Okay, number 30. An isosceles triangle ABC with base BC of length 23 centimeters, points P and Q are chosen on side BC with BP equals QC equals 9 centimeters. All right, let's just start drawing that. So triangle ABC, and BC is the base, so that means these sides will be the same. And this is 23 centimeters. P and Q are chosen on side BC such that BP equals QC. So BP equals QC equals 9. So then this will be 5. Your segments AP and AQ trisect angle BAC. And what is the perimeter of ABC? All right. So the obvious thing we can do is apply angle bisector theorem. So if we just look at APC, then the ratio of AC to AP will be 9/5, right? So let's just call this X. So this will be 5/9 right here. My diagram is kind of messy. Um, and then by symmetry, this will be, or not, like, because both sides are the same, and by symmetry, I guess. This will also be 5/9, right? All right. And then we can apply Pythagorean theorem, I think. So if we draw this line right here, this side will be 5/2 plus 9. And we also have, or what? Oh, okay. We can apply the Pythagorean theorem 2 times. So one to find this in terms of x, and then another to solve for x in the smaller one, right? I think that should work. So to find what this is in terms of x, we will have 5/2 plus 9 squared, or x squared minus this, rooted, right? Yeah. And then, it will be, what is this? Will be just 23 squared over 4. Okay, and we'll just leave it like this. And then we applied the Pythagorean theorem again with the smaller triangle, right? So then we have x squared minus 23 squared over 4. This will be subtracted from 5/9 x squared. And this has to equal 5/2 squared. Okay, and then this will be 25 over 81 x squared minus x squared plus 23 squared over 4. And this will equal 25 over 4. These aren't very nice numbers. Alright, whatever. So we're gonna get x squared minus 2581 x squared will equal 23 squared over 4 minus 25 fourths. So then we'll have oh gosh. Then we'll have 56 over 81 x squared equals 529 minus 25 over 4. I think that's right. And then we'll have 56 over 81 x squared equals 504 over 4, which is equal to 126, I think. So then we have x squared equals 81 times 126 over 56. So we can take it out 2. 63, and this will be 28, and we can take out a 7. So then we have 9 cubed over 2 squared. So then this means x squared, or sorry, x will equal 9 root 9. Oh, okay, that's actually good. Okay, yeah, this is probably right, because root 9 is just an integer, right? So that's nice. So then we have 27 halves. Okay. If x is 27 halves, what does this mean? This means that those two sides will be 27, and that is 23. Okay, and this will be equal to 50. Oh yes, the answer is 50. Okay. So the numbers were pretty bad, but it actually worked out. Oh, what did I do? So I made a perpendicular segment right here, and I applied the Pythagorean theorem twice with this triangle and with the smaller triangle. I'm not sure if my way is the best way because the numbers were pretty bad. I don't know. What way did you do it? Oh, same way. Do you have anything to say, Bill?
Uh, I mean, this is a wacky problem. So, nothing really that much to say, I guess.
Did
I
we do it this way in our solving?
I think we did, yeah.
I don't know. I feel like I don't remember having like
Well, we did
numbers
this two
this
weeks ago,
bad.
so that was quite a while ago. We did this 2 weeks ago.
Oh, dang, 2 weeks.
Yep.
All right. Yeah, I don't remember everything that well. All right. Um, it's 8:29. Should we do some target? I don't know.
Should we? It's 29 though. Like, should we?
We can just do the first few problems. That should be fine. Target was easy, I think.
Yeah.
Oh, what the heck? No. Yeah. All right, let's try to get through a few problems. So, yeah. All right. In September 2010, the U.S. Bureau of blah blah. I'm not gonna read that. Began to print $1 bills in sheets of 50. Before that, currency had been printed in sheets of 32. When printing 50 bills per sheet, how many fewer sheets are required to produce that many bills than when printing 32 bills per sheet? All right, this one is really easy, especially since you have a calculator on target. Um, you're just gonna divide you're gonna divide this number by, oh sorry, 32, and then you're gonna subtract it from this number divided by 50, right? Yeah, yeah, I guess national sprint is pretty hard, I guess, like with a time limit. Um, maybe if we had good days, we would do fine. If we didn't have like a bunch of computational errors. But you can see the score distribution on the sprint scores. It's actually not that like big. Like there are actually a ton of people who don't do very well, honestly. So like even if you make a 15, that's like you're placing like middle of nationals. So I don't know. That's pretty good, right? If you're placing like middle of nationals. So yeah. I don't know, I think 15 is um is gettable. Um the 30 guy is pretty insane. The 30 guy. All right. Okay, let's just do a few more target. Set A can for this I got what 648000. Yeah, That's the answer.
Also, if you're
All right.
interested, there was one problem that nobody got right.
Oh yeah, we'll talk about that next meet.
Yeah, next me, we'll get to that
Yeah,
problem.
so someone got a perfect individual score. So they also got perfect in target. They got perfect in target and they got 30. I think it's Edward Wan, right? Because he placed first,
Yeah,
and then
probably.
Luke got second. No, wait, no, this is countdown, I think, actually.
Well,
Yeah, this is countdown, I'm pretty sure.
uh,
So maybe it was Luke, I'm not sure.
could be. I mean, Luke's pretty overpowered.
Okay, set A consists of all integers A such that A equals p squared minus 1, where p is the prime greater than 3. What is the greatest common factor of all the numbers in set A? Oh, okay, this one's actually, I don't know, a decent problem. So we're gonna have the integers, it's gonna be like, so 25 minus 1, which is 24, and then it's gonna be 49 minus 1, so 48, and then it's gonna be 11, or sorry, 121 minus 1, which is 120, and you're gonna go so on. So, so what I would suggest for like starting doing this is just list out some numbers and then see like if you can get an idea of the factors. So so this is on 11. So on 13, it's gonna be 168. On 17, it's gonna be 288, and on 19, it's gonna be 360. Um, and if you divide all of these, you can actually see that 24 divides into all of these. 24. So yeah. So after seeing this, we should try seeing if we can actually actually prove that it is 24. Or maybe see that it's not 24 and then we do something lower. So 24 is 3 times 2 cubed, right? So we should try to prove that this is in all of them. So what we should do is we should look at p squared minus 1 mod 8. So if it's always 0 mod 8, then that means it's always going to have 2 cubed as a factor, right? Okay. So we should look at the mods of p mod 8. So we should look at p mod 8. Okay. So p has to be prime, right? So p has to be 1, 3, 5, or 7 mod 8 because it cannot be the even numbers. And then we should look at these numbers squared. If we have 1 squared, it will be 1 mod 8. If we have 3 squared, it's 9, which is 1 mod 8. 5 squared is 25, which is 1 mod 8. And 7 squared is 49, which is also 1 mod 8. So what is this saying? This is saying no matter what prime you have squared, it will always be 1 mod 8, right? And then we're taking a minus 1, which means what? Which means that will always be 0 mod 8, which means what? It will always have a factor of 2 cubed. Yeah, now take mod 3. We see if mod 3 is we see if all of them are 0 mod 3. And this will tell us whether it's 24 or whether it's 8, right? So we can have 1 or 2 mod 3, right? It can't be 0 mod 3 because then it would be divisible by 3 and primes can't be like that for p. And then we look at p squared. So p squared will either be 1 or 4 mod 3, but that's just 1 or 1 mod 3, right? So what does that mean? P squared minus 1 will always be 0 mod 3, which means what? It will always be divisible by 3, right? So the answer actually is, sorry, 24, which is pretty big, right? Yeah, the answer is 24. I think this is a decent problem. I kind of like it. But yeah. All right. It's 8:38. We're gonna end here for today. Um, yeah. Thanks for coming. Today was pretty rough. Hopefully, I don't know, we don't make as many mistakes as we do today. Um, we'll continue from this next week, and yeah. All right. If you don't have any more questions, you can go ahead and leave. Goodbye. Thanks for coming.